This is joint work with Sergei Avvakumov from Tel Aviv University, Marek Filakovský from Masaryk University in Brno, from Jakub Opršal in Birmingham University, and Uli Wagner at ISTA. So the standard coloring problem, so deciding whether or not a given graph is three-colorable, k-colorable, is a classical NP-hard problem that has been studied. One of the original one proven, one of the original one for which was proven hardness in colourable problem. Therefore, a lot of possible relaxation have been studied. One such idea is that to try to approximate a problem. So, suppose you're given a three-colorable graph G. Can you find k coloring for some suitable bigger constant number of color that is bigger? So k than 4. We are interested more in the decision version here. So if we fix constant k bigger than 4, and we are given a graph G that we have to decide whether or not it's three colorable or not even k colorable. Where we are promised that basically we're never given as an input something that is k colorable. So that's where the simplification comes in. We don't have to decide whether or not the graph is k colorable. We have just to determine whether it's three colorable or not even k colors are enough. This has been a surprisingly tough problem to study. So what is known is that if we try with 4 colors, this is NP hard. Recently has been expanded to 5 colors. They are conditionally hardness results for all k, assuming different version of unique games conjecture. And if we drop the requirement to be a constant number of colors, then the best known polynomial result is for slightly less than n to the 1 over 5. Okay. More generally, this can be thought as a graph homomorphism problem. So what is a graph homomorphism? Well, if I have to given a graph G and a graph H, a graph homomorphism is a map between the vertices such that any edge is mapped to an edge. So any two vertices there form an edge in G, form an edge also in their image, form an edge in H. Why do I call it a generalization? Well, because giving a k coloring of a graph is exactly as prescribing a graph homomorphism into the clique, into the full graph on k vertices. So, for example, here, prescribing a graph homomorphism from the graph on the left to the clique on 3 vertices on the triangle is exactly the same as prescribing a 3 coloring, as assigning a color to each vertex, such that there is no monochrome edge. In this setup, we can ask a more general version of the approximate graph coloring in question that we talked about earlier. That is the promised graph homomorphism problem. So, it's the following decision problem. That is, in input, you receive a graph I, and you have to answer yes if the graph maps to G, and no if it does not even map to H. So for a given template G, for a given pair of graph GH, such that there is none. Why this is called promised graph homomorphism? Because basically it's finding whether or not, deciding whether or not a graph homomorphism exists with the promise that it will never happen that I is an input that fits somewhere in between. So it might not map to G, but it does map to H. So this, in theory, might simplify theoretically the problem or with respect to the graph homomorphism, with respect to the general coloring problem. A very well-known conjecture is that actually this does not help. So if G and H are non-bipartite graph with G maps to H, then the promised constraint satisfaction problem. PCSP stands for promised constraint satisfaction problem. That is the more general framework with a more general class of problems where this graph homomorphism problem falls into. And since we're borrowing the terminology from there, and we're using methods that are come from those more general theory. So if either G or H is bipartite, then the problem is actually solvable in polynomial time, and that's pretty easy to see because a graph can be mapped into a bipartite graph, even only if the graph itself is bipartite. So if I'm given an input and one of the two, either G or H, is bipartite, I can just check whether or not the input is bipartite and answer yes or no accordingly. So in this case, the problem is easy. So the conjecture is basically this is the only case where it's easy. So anywhere else, the problem is NP-hard. What do we know about it? Well, in general, very little. Very recently, by Krokhin, Opršal, and Givny, they proved that for any choice of, for any possible 3 colorable non-bipartite graph G, then the corresponding PCSP with G with K3 is NP-hard. So the problem is to distinguish between any G coloring, any graphomorphism into G, or being 3 colorable is NP-hard. And our results fits into this line of research and is exactly the same thing for 4 colorable graphs. Now, if I have a 4 colorable non-bipartite graph G, then the corresponding promise graphomorphism problem, so of deciding whether or not it given input graph is G colorable or not even 4 colorable, is still NP-hard. It extends the previous results, the previous known result, the previous known case for K3, because we are basically strengthening the promise, because anything that was 3 colorable is also 4 colorable. So we cover a strictly bigger class of problems. And it's proven via very similar, the proof is also very similar. The proof uses the same, basically, topological idea, but with a much more sophisticated topological tools. So it is still topological in nature, but requires much more careful analysis, so a much more careful usage of topological tools. So let me give a rough outline of how the argument goes, and then we'll expand on each step later. So the first observation that we can make is that it's actually enough to show it for only odd cycles. Because why is that the case? Well, because if G is non-bipartite, that means it contains an odd cycle, and therefore we can assume, basically, if you substitute G by the suitable odd cycle of the suitable length, we are basically strengthening the promise. Any graph that is colorable for the odd cycle will be also G colorable. So we are basically solving a problem that is potentially easier. So if this potentially easier problem is still NP-hard, therefore also the bigger one, the problem with G will be NP-hard. So we can, it's safe to assume that a G is an odd cycle. Okay, so the algebraic theory of promise constraint satisfaction problems tells us basically that we should look at its polymorphism. So the complexity of the problem is actually governed by the polymorphism. What are polymorphism? I'll discuss it a bit later, but they are just graphomorphism between the power of the cycle into K4. So we need to study basically this polymorphism. This polymorphism have a quite complicated structure. They're not very easy to understand, but we can use topology to filter out some noise. So via topology, we basically can associate to every polymorphism. We can associate like a linear map from Z to the N to Z that basically with some non-degeneracy condition, that is this odd condition that the sum of the coefficients is 1 mod 2. And that respects the minor condition. So you preserve taking minor. We'll discuss it once again this a bit more in detail later. But this is not enough to get hardness. But if we with a bit of a combinatorial argument, we can show actually the number of non-zero alpha in each expression is actually bounded. It's at most up to a constant L squared, that is the length of the odd cycle, and this is independent of N. The constant is absolutely independent of N. Therefore, we get basically what is called technically bounded essentiality, and that is a hardness criterion that follows from the algebraic approach to PCSP that we'll discuss in a bit of detail later. So let's start with the algebraic machinery that we're going to need. So the first idea is that what do we mean by power of the cycle? Well, if I have to graph one of the possible ways to do the product is what is it's called the tensor product, the categorical product, that is given to graph G and H. Their product is the graph that has vertex set, the product of the vertices, and edges. Two vertices U1 V1 and U2 W2 form an edge if and only if U1 U2, so the two vertices in G, form an edge in G, and the two vertices in H, so W1 and W2, form an edge in H. So this is the product. what is the power? The power is just the product of graph with itself n times. And then what is a polymorphism between two graphs? A polymorphism of certain arity n is just a graph homomorphism from the nth power of G to H. And we'll denote by the set of all polymorphism by polymorphism pol GH. That will be useful later. One quick observation here, in the definition of polymorphism, we are talking about graphs, but in general, this notion makes sense also for sets more generally, or for any object that has a notion of power. So as long as I can take a power, and then I can define what a polymorphism is. I will use once again this a bit later. Okay. Why are they interesting? Well, because what can we do with a polymorphism? Well, with a polymorphism, we can build new ones. Because if I have a polymorphism, I can identify some coordinates, I can add some dummy ones, some non-essential ones, and create a new one. So let's say, for example, here, let's say I'm given a polymorphism of arity 3. Then I can build a new one that has arity 5, and I just need to tell you how to evaluate it on a tuple, x, y, z, u, v, and let's say I evaluate it f of x, u, x, for example. This, no matter what I choose, will be a polymorphism. Formally, what I've done here is what is called, I've taken a minor. So if I have a polymorphism and I fix a minor map from the set with n element to the set with m elements, so the set of coordinates, the pi minor of f, it's a new polymorphism from it's a polymorphism from G to the M to H that is defined by using pi to choosing coordinates according to pi. What does it mean in practice? Well, in the previous example, if I choose pi to be the map from 3 to 5, defined as that we send 1 and 3 to 1. So on the first and third position of our new polymer of so exactly. So 1 and 3 to be 1 and pi to be 4. Then basically we evaluate using first coordinate. In the first coordinate of f, we evaluate with the first entry in a tuple. On the third coordinate, we also evaluated the first entry. On the second coordinate of f, we evaluated the fourth coordinate of a tuple. So G, the defined polymorphism, is exactly the pi minor of f. What is not, as we see here, not all coordinates of G are interesting, like Z and V, for example, here, or Y, do not influence the output of G whatsoever. So in some sense are non-essential, are dummy Pareto, while X and U, in some sense, might be important. So how do we formalize this notion? Well, it's what is called the essentialarity. So if a polymorphism G that has some arity n, it has essentialarity at most k if it is minor of some function of some polymorphism of arity k. So it cannot have more than k interesting variables in some sense. And here, for example, the essentialarity of G is at most 3 because we have shown that G is a minor of a function of arity 3, but in particular, we could show that G has essentialarity 2, but it's not important for us. It's just that it has at most 3. Okay. What we said here is that basically the polymorphisms of two graphs form a set of functions that is closed under taking minors. In general, whenever I have two sets, and I take a non-empty subset of all the possible functions between all the possible polymorphism between two sets, and I take a subset that is non-empty and closed under taking minors, this is what is called a minion or a function minion, if you want to be precise. Given a function minion, once we have a minion, once we have an object, we want to define the corresponding notion of a map between these two objects. So what is a minion homomorphism? A minion homomorphism is a map from a minion M to a minion N that basically preserves arity. So if something, if F had arity N, then so eta of F has arity N, and commuting with taking minor. So if I first take the minor and then go through with eta, then it has to be the same as first going through and then taking the minor. Why is this relevant for us? Well, the algebraic theory, the algebraic approach to Promise constant satisfaction problem tells us if we have two graphs, G and H, such that their polymorphisms have a minion homomorphism into some minion B that has bounded essentiality. What do I mean by that? It means there is a global constant n, that some fixed constant, such that every function in the minion has essentiality at most capital N. So there is a global constant that does not depend on anything, that depends on the some fixed constant such that every function in the minion has essentiality at most n. Then the original, if I can map the polymorphism of GH into such a minion, then the corresponding promise constraint satisfaction problem, the corresponding graph homomorphism problem is NP-hard. And this would be the source of hardness in our proof. How do we go about building such a minion homomorphism? Through topology. So we'll need to introduce a couple of concepts. So the first concept from topology that we'll need is the simplicial set. You might be familiar with a simplicial complex, and a simplicial set, in some sense, it's a generalization. Similarly to a simplicial complex, a simplicial set is also a combinatorial way of how to build a space starting from vertices and then edges and then triangles and higher dimensional simplices by gluing them together, except we use more general functions to glue them. So instead of having this strict restriction that they must share a face and then you cannot glue things that have different dimensions, that have dimension, there is a gap in dimension more than one. That is, so for simplicial complexes, you only glue an n-dimensional simplex to a face of n-1 dimensions and so on. So it's very rigid. Informally, when you have a simplicial set, we basically say that every n-dimensional simplex, we see it as labeled by some ordered set. So from these vertices are labeled by 1 to n. And then we glue simplices. We are free to use any linear map that is given by a weakly monotone map between vertex sets. So it's much more flexible, but it still maintains heavy combinatorial. We still maintain a heavy combinatorial control on how these things are glued and how the space look like. Let's see an example here. We have a simplicial set structure that we call sigma 2 that will be used throughout on the standard sphere S2. And how does it look like? This has two vertices, has two non-degenerate edges, so two interesting edges that are the yellow one and the blue one, and has two non-degenerate triangles, that is the, once again, yellow and blue. And how they're glued? Well, the yellow one has goes from the yellow vertex to the blue vertex, the blue edge goes from the blue vertex to the yellow vertex, and so on. In particular, note that it has like a built-in antipodal symmetry, so we can swap blue and yellow and stay and be an automorphism. Okay, what is formally the simplicial set is a collection of the following data. First, it's a collection of some pairwise disjoint sets, x1, x0, x1, x2. Basically, we can think of these sets as the collection of n simplices of x. And then for every pair of weakly monotone maps between the potential vertex sets, so the z elements of the set of with n+1 elements set to 0 to n, there is a corresponding map that goes the other way. So from the n simplices to the m simplices, such that the identity corresponds to the identity and the composition corresponds to the composition. The technical definitions, it's a bit complicated. It's not particularly important. You can think of them as simplicial complexes with much more flexibility in how we glue stuff together. And what is a simplicial map? Well, a simplicial map between two simplicial sets is just a collection of maps between the sense. Basically, it's a collection of maps that sends n simplices to n simplices, such that the gluing maps behave nicely with respect to this function. Okay. How does it look like here, for example? Any simplicial map. So if you fix some simplicial set X and we want to build a simplicial map into sigma 2, well, this is just prescribing a two-coloring of the vertices of our simplicial sets, such that every simplex has at most two alternations. Why is that the case? Because here, if you look at it, every simplex in sigma 2 is uniquely defined by its ordered list of vertices. So, for example, let's say the edges. You have the edge that is yellow-blue, that is the yellow edge, and then you have the edge that is blue-yellow, that is the blue edge. And each of them is uniquely defined. So once I give a two-coloring of the vertices of x0, I have defined on which simplex each of the n simplices of x0 of x must go, that is the unique one that has that list of that ordered list of vertices. Why is that has most two alternation? Because every simplex here, there is no simplex in sigma 2 that has 3 alternations or more. So if you want to map simplices to simplices, we must have at most 2 alternations, no more than that. Okay. How does this relate to graphs? Well, it relates through what is called the Hom complex construction. The Hom complex is a well-studied construction in topological combinatorics. And what does it do? Well, it takes basically codify the structure. If I have two graphs F and G, and it codifies the structure of the homomorphisms from F to G into a simplicial set that we call Hom FG. How do we use it? Well, we fix some small test graph, in particular the smallest of them all, that is the edge, and we study how the Hom complex K2 behaves. The definition is a bit technical. I don't want to go into details here, but the key properties that we'll need are that for any fixed graph, Hom K2G has a baked-in Z2 symmetry. That is, it's inherited from the fact that the edge can be flipped. You have the vertex flips involution of the edge, and this becomes like a simplicial set symmetry of the whole thing. And this will be respected throughout the whole topological argument. I will not necessarily always mention it, but it's always assumed, and it's a key part of. It's a technical assumption that is key for our proof, but it's not particularly useful for the explanation. Whenever we have the second property that we use is that whenever we have two graphs, G that maps to H and a map between them, then the corresponding continuous map, corresponding simplicial map, there is a corresponding simplicial map. So in some sense, the construction of K2 is functorial, if that makes sense. If this word makes sense. Moreover, up to homotopy equivalence, so up to a suitable notion of topological equivalence, the Hom complex commutes with taking powers. So the Hom complex, if I take first G to the N and then take the Hom complex, that is homotopy equivalent to first taking the Hom complex and then taking the topological power or the simplicial power. Finally, for the cases that we're interested in, so when G is an odd cycle of arbitrary length, or when G is the clique on 4 vertices, we can actually explicitly determine who these simplicial sets are. When we have an odd cycle, then we have what we call gamma for L. It's just notational. That is, topologically, this is just a circle. This is just S1 with the standard, where the Z2 symmetry is the standard antipolarity. This here, for example, is the simplicial structure that you get from Hom K2 C3. In the case of the clique, what you get is topologically it's a sphere, S2. This simplicial structure is a bit more complicated, but we can simplify it because we have a simplicial map that is antipodal with respect to the symmetry that maps into our simple simplicial set structure that we built earlier, sigma 2. And such a map, once again, it's given by a 2 coloring, and here is one such example. It's easy to check that does not have any 3 alternations. So it is a valid simplicial map. Okay. How can we build a minion homomorphism? We want to build a minion homomorphism somewhere in a minion that it's called Z2 that I'll define later, but how do we do that? Well, we start with a polymorphism from the power of the odd cycle into K4, and to that we have a corresponding. We take the Hom complex and we get a corresponding symmetry preserved simplicial map that goes from the nth power of gamma for L, into Hom K2, K4. Topologically, this is a map from a n-dimensional torus, so the nth power of the circle, into S2. Understanding such maps up to homotopy is still quite complicated. It's closely related to problems that are actually like undecidable. They're very complicated topological problems. The nice thing is that algebraic topology has been studying these type of problems since forever, basically. And so there are a lot of tools. In particular, what we can do is that instead of going into sigma 2, we can simplify further. and go into Y, that is like some space that we call Y, that is some nicer from a homotopical point of view, that is technically what's called an Hilbert plane space, but it's as far as we're concerned, it's just like a simpler, nicer simplicial sets that extends sigma 2. Why do we do that? Because now we understand. Now we can explicitly compute who these maps are. And symmetry preserved maps from the torus to Y up to homotopy, this can be classified by using suitably defined topological invariants that we are called the degrees along the ith coordinates, so the I. And the definition is not important. The key observation is that any map from the torus Tn to Y corresponds to one linear map from Z to Dn to Z that has this odd condition. We call such a collection of maps, of linear maps from Z to Dn to Z that has this odd property. We call Z2, and this is a minion. It's pretty easy to see. And the key observation is that the assignment that for a polymorphism of the odd cycle turns into a topological map and then computes the corresponding linear map on Z2s. This respects minor, clearly respects arity, therefore it's a minion homomorphism. Okay. This is not enough to get hardness because we need to show that such a minion, the minion Z2 itself does not have bounded essentiality. It has arbitrary high, has maps with arbitrary high arity, essentiality. But what we will show is that the image that we obtain in here actually still has bounded essentiality, and that's how we will get hardness. We'll go through because these maps that we get, they're not just generic topological maps within tori into Y, but they are maps that come from a specific simplicial set structure that we can control. And this has some combinatorial constraints in what can happen. In particular, the first observation that we already made is that any simplicial map, giving a simplicial map from some simplicial set X into sigma 2, it's the same thing as giving a two coloring of X of the vertices such that every simplex has at most two alternations. The second observation that we can make is that any simplicial map that goes from the torus, from the standard two-dimensional torus into sigma 2, such that the first coordinate is relevant. So the degree of the first coordinate is 1. That means that it is, in some sense, an essential coordinate. So we have that something happens there. Well, we have that at least one horizontal edge is color swapping. What does it mean? It means that if one coordinate of this torus, if the first coordinate, let's say, of this torus is interesting, has some influence on the outcome, then it cannot be always constant along. You cannot have only monochrome edges along this horizontal line. So that means, in some sense, that means that at least 1 over L squared, so we have one edge out of all possible L square edges, at least one edge is color swapping. That means roughly 1 over L squared edges is color swapping. Now we go back to our bigger dimensional, to our high dimensional torus. That's actually what we're interested in. And now what we can do is we can take diagonal slices along the coordinate that are interesting, like here. And here we get that at least one edge in this diagonal torus is color swapping. But also we can shift a bit higher. This is once again a torus, in a two-dimensional torus in our bigger dimensional one. The first direction is still interesting, therefore it does not touch any other edge that was covered before. So therefore we get a new color swapping edge here that was not counted before. And we slice it here. Higher, we get a new color swapping edge that was not counted before. We get a new one. Therefore, overall, we get roughly 1 over L squared fraction of the horizontal edges are color swapping if the horizontal direction is interesting, is essential. This does not work exactly as I stated because these slices are not, the slices that we take are not actually this nice because these do not work. But what we pay is that we pay a constant fraction. Basically, we cannot show that 1 over L squared is exactly 1 over L squared edges are color swapping, but just like 1 over for some constant 1 over CL squared fraction of the horizontal edge are color swapping. Okay. how can we use this to prove what we are interested? So we fix any simplicial map from gamma n L to sigma 2, and we want to show that it has to have at least at most O of L squared essential coordinate. Well, fix the essentiality of K, fix the essentiality of the function, let it be K, then we choose uniformly at random and simplex in the triangle, in the torus sigma gamma L to the n. Let's say that is u0 un, and define the random variable xi, that is 1 if exactly the edge between the UI and UI plus 1 is color swapping, and 0 if otherwise. What happens to the total sum of these variables? Well, what's the expected value? The expected value of these sums, we know that for every direction where something happens, so for every essential direction, for every there are k of those, we should have at least 1 over CL squared color swapping edges. Therefore, we should expect that the expected value of this variable by linearity has to be at least k over CL squared. At the same time, though, we know that F is a simplicial map. Therefore, no simplex has more than 2 color swaps. 2 color swapping edges, because it's a map into sigma 2. But this sum is exactly the total number of color swaps in the simplex sigma. Therefore, we have that the value of this function is actually hard bounded by 2, because it comes from a simplicial map. Therefore, 2 has to be bigger than k over CL squared. Therefore, k is smaller than 2 CL squared. And note that this does not depend on the dimension of the torus n. And we showed then any function. So if you have a polymorphism from any function, if you pick a polymorphism from the odd cycle into K4, we obtain a simplicial map from the torus gamma n L into sigma 2, and therefore this has essentiality at most L squared up to constants. Therefore, the image through this minion-homomorphism has to have bounded essentiality, and therefore the original problem was NP hard. So this concludes our proof. And what do we go from here? Well, the natural question would be: can we say something? Can we use these topological methods to prove hardness for graph into K5? And this, by a simple dimension argument, shows that as it is, like as we are doing things now, this cannot work. It requires new topological ideas by a simple dimension argument. The minion that we obtain through topological equivalence, multiple equivalence, collapses to just constant. So it requires new topological idea. A little bit more hidden, but throughout all the discussion, there is this antipodal symmetry that I've not mentioned very much, but it's key. It's help us to prevent this collapse, this collapse that happens in the K5 case. It helps us avoid in the K4 case using this symmetry. Therefore, all the topological proof at the moment work with symmetry, work only with symmetric templates, because we need to have this intrinsic symmetry there to prevent us from collapsing. Can we say something? Can we make topology work for non-symmetric templates? So, for example, oriented graphs. That is clearly a very interesting question. More generally, what kind of templates, not only pair of graphs, but also more generally relational structure, for more general promise constraint satisfaction, which templates can be studied topologically? And all these constructions are actually categorical in nature. That I've not mentioned here. I've been hiding it, but everything here can be seen through the lens of category theory. And one natural question is that can we use some more general construction through category theory to help? So substitute, instead of using home complex, that is just one possible construction, use something else, for example, generalized nerve functors or something along those lines. Will that help? That is clearly a very interesting question to study. And with that, I thank you for your attention.